welcome to our mini project presentation for CSE106 Discrete Mathematics. I'm Zarin Shuchona, and today, along with my team members Utsha and Wasif, we are presenting our analysis on time complexity and graph theory simulations. This project was conducted under the guidance of our instructor, Dr. Nafis Sadiq. Now let's look at the problems we are addressing in this project. For part A, we are investigating the empirical time complexity of linear search, where we would test the algorithms on an array of different sizes, plot a graph of average time versus n, add a trend line, and then compare the observed results with the theoretical average case complexity of linear search. For part B, we are simulating a friendship graph using an undirected graph model. Our goal here is to understand how theoretical complexities translate to real-world runtime and how social networks behave mathematically. Our main objectives in this project for part A is to implement linear search and test it on increasing input sizes to observe its behavior and to compare the experimental results with theoretical expectations using plots and a trend line. As for part B, to model a social network using adjacency matrices and analyze the properties such as the handshaking theorem and connected components as the network grows. Now I will hand it over to Wasif to walk you through our linear search experiment.
Thank you. Let's dive into part A1. To determine the empirical time complexity of linear search, we implemented the algorithm using Python. We didn't just test it once, we followed a rigorous scientific methodology. We generated random arrays of integers for 5 specific sizes, 10,000, 20,000, and all the way up to 50,000 elements. For each size, we performed 1,000 distinct searches for random targets. This was crucial to average out any system noise and get a true average case runtime measurement in milliseconds. Here you can see the results of that experiment. On the x-axis we have the input size n, and on the y-axis the average time in milliseconds. We plotted our data points and added a trend line, which is the red line you see across the graph. As you can observe, the relationship is a straight diagonal line. Therefore, as the input size increases, the search time also increases proportionally. I have also provided results of that experiment where we can see from the analysis input size increases with the search time. Also, real-time analysis for the average search time have also been provided in milliseconds in the following slide. As a result, this linear growth perfectly matches the theoretical expectation. In theory, we can all say linear search has a time complexity of big O n. Our empirical data validates this. Doubling the input size roughly doubles the search time. This confirms that for unsorted data, the algorithm performs exactly as predicted by discrete mathematics theory. Provided is the linear search code used for this problem. And now, Utsha will explain our simulation of social networks in part B.
Thank you, Wasif. Moving on to part B1, we simulated a friendship graph to model a social network. We used an undirected graph represented by an adjacency matrix. In this model, nodes represent user and age represents bidirectional friendship. We ran simulation for networks ranging from 500 to 2,500 users. For each network, we randomly generated friendship ages, programmatically calculated the degrees of all vertices to verify the handshaking theorem, confirming that the sum of degrees equals twice the number of ages, and finally, we counted the number of connected components. Please take a look at this graph. It plots the number of connected components against the network size. You will notice a downward trend as we increase the number of users while maintaining random connection. The number of isolated groups or connected components actually decreased. Now let's talk about the results. First, we look at how the degrees change for different values of n. As the network gets bigger, users becomes more connected. Next, we confirm the handshaking theorem. This means the total degree of all nodes is twice the number of edges. Lastly, we notice that as n increases, the number of connected component decreases. This tells us that bigger networks slowly join together and form larger connected groups. This is a fascinating observation that aligns with the small world phenomenon and the emergence of a giant components event with random friendship. As the network grows, smaller groups tend to merge into one massive interconnected cluster, much like we see in real social platforms like Facebook or LinkedIn. In conclusion, our short project successfully verified that linear search follows time complexity and that random graph simulation can accurately model social network behaviors. Here is the source code of our friendship graph, and thank you for watching our mini project. Thank you.